Hey everybody, thanks for hanging in there. My name is Noah Zoschke. This is a talk called Running Heroku on Heroku. And of course, we're here at Aloha Ruby. And yeah, thanks to all the organizers and all the speakers and all of you guys for making a really great event. So the slides for this are online if you ever want to reference anything. So I would assume most of you are familiar with Heroku as Rubyists, but just a quick background. Heroku is a cloud application platform as a service. So we used to say we're a Ruby application platform on service, but of course, we have opened this up to other languages, Python and Java and Node.js. And one of our taglines is run anything and see everything without servers. So one of the goals, certainly a personal goal of mine, but a goal for our platform is to just destroy the concept of a server. It's you are application developers, we're all application developers, don't really want to deal with the traditional operations involved of setting up servers, setting up databases. We just want to get our apps online. And so a more low-level way that I think about this personally as a platform engineer is that we're developing a distributed Unix. So this is this kind of grid of application servers, all based on Linux and open source. It's Ubuntu-based. And I consider Heroku as kind of this operating system layer to interface with just this pool of computing. And I suppose that's the cloud, but it's also just some servers in Amazon. And so this talk, it's something I just think kind of an interesting computer science problem. The concept of bootstrapping and how that relates to self-hosting. So not talking about Twitter Bootstrap as a design tool or anything like that. This is, if you guys caught Glenn's talk a minute ago, this is kind of my strategy for keeping the designers away. We can just go really deep into the computer science here and understand as computer scientists what some of these low-level primitives are for programming. But we can step back for a second. Bootstrapping, it's a generic word. It has a lot of applications. First came around in the 19th century where people actually wore boots and had straps on them. And the first meaning of this, it was something that was impossible. It's to raise or better oneself by one's own unaided efforts in a far-fetched manner. So this was something, it was a term given to like traveling salesmen that had perpetual motion machines or get-rich-quick schemes. These guys were referred to as bootstrapping, and it's just something you can't actually do. You can't obviously lift yourself up by your bootstraps. Early literary references, Baron Munchausen, who was an adventurer running around, and his horse got stuck in the mud, him on his horse, and he was able to save themselves by lifting himself up and his horse up by his ponytail. So I suppose that's ponytailing, not bootstrapping, but same concept. And at some point, the meaning shifted a little bit in the 20th century, and it actually became a positive term, which is how we know it now. So this is now it refers to a self-sustaining process that can proceed without external help. And there's a lot of different domains that this term is applied to. So one is socioeconomics. Anytime we're in a political season, we have these politicians all trying to out-bootstrap each other. I came from this poor city and worked really hard, and it's the American dream, and pulled myself up from my bootstraps. Business, if you guys read 37 Signals, bootstrap, profitable, and proud. It's a concept that can apply to software companies or any company really, where you get this company off the ground, you don't need a ton of VC, you just have a really solid idea and a really good work ethic, and put a little bit of your own money and sweat into this thing and lift this thing up and get a good, healthy lifestyle business going. Statistics, linguistics, this is an interesting one. Refers here to the process which children acquire language. Kids start in a blank slate. They can obviously hear things but can't speak, and somehow there's this process of bootstrapping the ability to both talk and listen and understand. Similarly, biology, all your cells start out as these generic stem cells, and there's this bootstrapping process by which they acquire specialization and turn into different types of tissue and so on. And of course, computers, which is probably the thing that actually brings us here. As I was researching this subject, it took a little while to connect this dot, but booting a computer, that's short for bootstrapping. Some of the original computers, you know, the old mainframes or whatnot, would have a big, giant red button on them that said Bootstrap. And this is the thing, you push it, and it turns on all the equipment, all the electronics at the right time, and sets registers, and so on and so forth. And you know, this is still something incredibly important, but we don't even have to worry about it anymore. It's just, you know, you just open your computer or press the button, and it turns on. But there is very, very complicated and intricate things happening inside computers when they boot. And so then there's also another computer science application here, which is compilers. So I'm sure you all want to sit around and talk about compilers this afternoon instead of being on the beach. But so this, in compilers, bootstrapping, it's a process by which a simple language is used to translate a more complicated program, which can handle an even more complicated program, and so on and so forth. So similar to booting of a computer, we now have, you know, these beautiful interpreted languages like Ruby, but there's this really complicated set of steps that had to happen for us to actually just get a Ruby terminal and be able to type, you know, hello, print hello world or puts hello world and get this thing to happen. So somewhere you could trace all this stuff back, and there's, you know, Ruby is compiled with C, and C needs to be bootstrapped by another binary or a linker or an assembler or so on and so forth. And luckily, where we sit now, we don't, again, have to think about all this too often, but it certainly is an interesting problem. So there's a chicken and egg problem here with bootstrapping a compiler, and which, you know, you can't, again, same way with Bootstrap, you can't actually just lift yourself up from nothing. So we have to develop some strategies to handle this. So probably one of the earliest ones, again, back in the mainframe days, was to hand compile. As you would say, well, I have this system, and I know it needs to, you know, interpret this string of characters. How do we get this off the ground? Well, somebody was physically inputting bytecode one little operation at a time and building kind of the simplest compilers or the simplest translators. So then we could use the results of that. You know, if we got a little Fortran compiler that was written in handwritten assembler, then we could use Fortran to start building other things. So we can build a compiler for X and Y. And then now we're getting going here. So now we might have an old version of one of these things. We have an old Lisp interpreter, and we can use that to build another Lisp interpreter. Or a new version of the interpreter. So it can start moving along. And another strategy, you know, is a simpler restricted version, something with a subset. So if you guys follow Rubinius, that's a great example. Or I'm more familiar with PyPy, actually. That's an example of this last one. PyPy, it's a Python written in Python. And there's this little subset called RPython, restricted Python, that's simpler than the whole Python language, but still very powerful and expressive, and you can build up some tools like that. And so finally, you get to the holy grail of compilers here, a self-hosting compiler. So this is where, after this working Bootstrap procedure, we can improve the process a few times, or maybe many times, and finally get a compiler. We can rewrite the compiler in its own source language. So this, let's see, there's huge advantages here. So the example of this is, which we'll dive into a little bit more in a second, is say LLVM. It's a C compiler, or Clang. It's a C compiler written in C. And so Rubinius is another example of this, is a self-hosted language. And one of the big advantages, it's a human advantage here, which is the development can happen in this higher order language, in this higher level language. And it's nice, it's good for us that, you know, somebody working on Ruby core doesn't have to know assembly. We've seen through PyPy and Rubinius that this actually leads to like really surprising advantages in languages, which is, you know, you might think it wouldn't be as efficient to write Ruby in Ruby, but it actually turns out that it can be, just because it's so much easier for developers or for these maintainers to understand the concepts going here, and they have much more expressive tool, and that allows them to really focus on just kind of the big picture and some correctness, but simplicity, and there's a really interesting advantage there. Another one is that it's a non-trivial test of the language being compiled. So you say, we have this language, whether it's C or Ruby, and we can say pretty confidently that a language isn't very good if you can't write other translators or other computer-based translators in it. So saying that we can actually express a Ruby VM in Ruby is a good sign that Ruby is a sufficiently expressive language. And finally, it's a comprehensive consistency check. So there's no better test of a language and the system of programming and compilers than to have this self-hosted system. You can say the C language, this implementation of the C language can build another implementation of the C language. You can feel really comfortable that this specification, what this should do, and how it's implemented is comprehensive. So as I was, again, researching this, I wanted to do a kind of deep dive into this myself and kind of test one of these self-hosted tools and make sure it actually works the way you would expect it, and that I understand what's going on here. So I grabbed LLVM. Are you guys familiar with this? You should be. If you are Mac users, it's replaced the tool chain there. But it's low-level virtual machine. It's this cross-platform, low-level virtual machine that has all these pluggable front ends. And it's really impressive software. It's kind of new, which 2000, it was a research project at UIUC. And it's slowly been giving GCC a run for its money, if not replaced it in a lot of ways. And its architecture is really solid. You get this low-level component, and then you can plug all these front ends to it, and so have many different languages, and it's really like a compiler framework. And Clang is probably the most popular part of it. That's the CLang, C, C++, Objective-C front end. And that's notable that it's the C++ compiler, Clang, is written in C++. So we're going to do a 3-stage bootstrap of this tool. So read the Getting Started Guide for LLVM. The Getting Started Guide is probably 100 pages of just crazy C compiler stuff. But I can kind of cut it all down here to 3 steps. So excuse my shell script, but the first one, we're going to build LLVM with GCC and G++. And then the next time, we're going to do the second stage, we're going to use the output of this first stage build, and now use the CLang, or the Clang compiler in Clang++. And we're going to do this twice in a row using the results of the previous one, and just kind of loop through these, and configure, make, install with whatever is specified. And finally, when we're done here, just kind of inspect the binaries. I'm sorry, we're going to make test. That's the important part, is run this comprehensive test suite. And so kind of an aside here, as I was playing with this concept, I was sitting in the coffee shop and getting a little frustrated with the Mac development tool chain these days. You have to go to App Store and download Xcode, but that's not enough. There's another plugin or something like that. So I'm like, oh, fine, I'll fire up Vagrant and do it in VirtualBox. But that's kind of a drag too. You have to download this box. It was a fresh laptop. And so then, of course, I remembered, well, I can just run this on Heroku. The Heroku, you might be familiar with it for running your web applications on the application servers, but these all have a very simple, it's like build essential in Ubuntu terms. So Heroku Dino has a GCC compiler that you can actually use if you care to. It doesn't really matter for running your web application, but it's kind of a nice thing to have for some stuff like this. So threw together the script, run it on Heroku. I think I got one running over here. It's kind of plugging along. It takes a long time to actually do this. And first, build in C with GCC. You can see here, using GCC, make test. The tests all pass. That's very good. So we think GCC is capable of building the Clang source code in a fashion that the tests for this thing will all pass. And then, so now we have a binary like this artifact of this first step. So we can use our stage 1 binary. So here, using Clang and Clang++, and we do this again. So here, an interesting thing to note is that Clang aims to be 100% backwards compatible with GCC. So it can actually, trick configure to think, oh, I do have the GNU C compiler, even though we are using something different. And sure enough, make and make test passes again. And if we do this a third time, the output's not here, but it'll pass one more time. So some interesting things to notice here. Finally, we can compare the binaries. And the stage 1 output and the stage 2 output, these look very different. And there's just a lot of crazy, strings is a funny way to look at binaries, but there's just a lot of different things here. But this is what we would expect. We've taken this source code of Clang, built it with GCC, and we expect that since the test pass, it actually works, but we wouldn't expect it to, GCC has very different semantics for actually building things. So we would expect that it would look different in terms of the actual binary representation, but hopefully that the tests are comprehensive enough to say that it's functional. But then between stage 2 and stage 3, where now we are building Clang with itself, we see very little difference between these binaries. So that's comforting also. And so you might, if you're looking closely, you might wonder, why do we actually need to do this third build? After we build it once, this thing works, it passed the tests. This thing works, it passed the tests. What's the third one for? And back to just kind of one of the reasons why we like self-hosted compilers. This is just one final test of actually the stage 2 binary. So it passed make test, but there's one really, really good extra test to do, which is just throw the whole source code of Clang and LLVM at it again and make sure it can actually build this thing one more time. And so the correct thing to do in this case is to throw away these other ones and use the stage 3 release. And now we actually have a self-hosted compiler binary that we bootstrapped from the ground up. So the self-hosting guy compiled Clang with Clang. This works. Very cool. So if you guys have read your Gödel Escher Bach, some of these concepts are referred to there. Certainly Escher understood something about bootstrapping. So here, we have the one hand drawing the other hand. And of course, we're not seeing here is the kind of initial bootstrap, which is Escher actually drawing this image. So again, so the self-hosted, this concept of self-hosting, so cool. Bootstrap compilers, self-hosts. But just like the term bootstrap, this has kind of a higher meaning. It applies to other domains also. So we saw this with the compiler, but it can kind of refer to any computer program that produces a new version of the same program. So compilers, kernels, this applies to that. Programming languages, again, Rubinius or PyPy, those are self-hosting. Revision control systems. Linus famously manages Git in Git. I would assume that was true of Subversion was managed in Subversion. Text editors, you'd expect most of the authors of Vim to probably actually use Vim to edit this application. And this is also an applicable metaphor for services. So drill into this for a little bit. So Heroku, we know a thing or two about services, run many cloud services actually, and many of these are self-hosting. So this is what I think about day to day. The compiler stuff is interesting, computer science, but how do we at Heroku apply these terms, and why would we do this? So there's a very simple first version of this concept, self-hosting, which is we run www.heroku.com on Heroku. It probably shouldn't surprise you much. I would guess you'd be surprised if we actually ran this on Slicehost or something like that. And this applies to pretty much all of our web properties now, the Dev Center and the blog and all that stuff. We built this platform for running websites. We should run our own websites on it. We should self-host them. And the motivations for this, for anybody that runs a product, I would assume you know that you really want to do this. It's called dog fooding. Eat your own dog food. If it doesn't taste good, either get used to it or make better dog food. There are huge efficiency gains here. So much like we had that efficiency gain in being able to write a C++ compiler in C++, at Heroku we can get the same efficiency that you may use for deployment. We can use that for deploying our own website. And separation of concerns. So the www self-hosted in its own corner. This kind of historically for Heroku is an interesting story. The beginning of the Heroku platform, Heroku, we have this giant monolithic Rails app called Core. And Core was pretty much everything. It's just this giant thing, and it has the website, and it has the API, and it has all these control surfaces. And it used to be if you wanted to make a change to the public-facing website, you had to deploy Core and alert all the ops guys, have somebody hold the hand. You might accidentally, a bug in the website could take down the API. Like, terrible, terrible idea. So split all these things up. Separation of concerns. And so we've applied this to kind of moving up the stack of our platform. We have an addons platform, and that also is running on Heroku. So not only is the addons website itself, and that has some background job hosting and stuff, but then we have built a number of add-ons, say the scheduler add-on, it used to be cron, that run on the platform. So now this is kind of moving up and testing the platform. We know we can run web applications, but we also want to run more complicated operations. So even though this still probably looks like a lot of your web applications, this is just a couple web processes and some rescue scheduler and so on and so forth. Moving up again, but still kind of the add-on services. We run a totally different cloud. It's its own Amazon box. It's called Heroku Postgres. And this whole add-on is built on Heroku. So now we're getting to some complicated stuff. This isn't just a web application. There's certainly a web front end. But all the provisioning of the database servers, all the monitoring, all the add-ons API is all a Heroku app. And this was the sort of thing, seeing the growth of this, where the dog food didn't taste very good for a while. It was really hard to do this. I remember working on this, and I'm like, man, Heroku, it's great for websites. It sucks for this. Like, I do just want to run this on a slice host. But like I said, if you don't like the dog food, find a better recipe. So slowly but surely improve the platform to handle a use case like this even better. But we can probably go even deeper. So this is like where the Heroku inception starts happening. These are just the Halo difficulties, if you haven't noticed. But to talk about that, I'm going to step back for a second and just kind of talk about the basic architecture of Heroku. So really what we have three main inputs to the platform. We here have the HTTP router. This is where all the web requests come in and get sent to the dynos or the application servers or the processes running your code. So this is where your customers come into the platform. We have the API. This is where HTTP requests come in and kind of talk to the control plane of Heroku. So things to scale your dynos up and down, to create a new app, to delete an app. And this is the Rails application. And then we also have, kind of famously, our git push Heroku. We have SSH traffic coming in. And this goes to the build system. So you do a git push. This is where then we build your code, whether that means bundle it, or since we do Node, you do npm install. And we build your dyno, store it in S3, and then we can run these at any given time on demand, whether you're scaling up and down, new servers, or idling and unidling. And so kind of a simplified, but actually fairly complete kind of overview of the inputs to our system. So I'm going to dive into the build servers, something that I work on a lot, but I also just think is a really fascinating use case. So here, the rectangles, these are servers. And if you recall, one of the goals of Heroku is to forget servers. And this applies to you for your web application platform, but this applies to me as an infrastructure engineer. I want to forget servers as much as possible, too. So the challenge is to take these compile servers that are kind of a worker pattern. They're running a work queue of just kind of guys sitting there waiting for a job to run it on this server. And I want to move this down to the runtime, to the process model, which is which is how the product actually works. And so I want to get these guys running in a Heroku app effectively. And there are some really, really important motivations here, more than just efficiency. This is where we get into, again, these kind of human benefits of this self-hosted vision. So if can't handle enough SSH traffic, need to boot up new servers. Well, we know that sucks. That's the old method. I just want to do Heroku scale. So I can get the effortless scaling of the platform. Really important one for all of us is this build and run symmetry. So if these are different servers here, we can get them very close, but there is always really subtle differences of, the software to run this needs a few different dependencies, and make sure those don't leak, because your application, when we build it, could accidentally get the wrong Ruby or the wrong gem here or there. We're really going for, it's something that I think we're all going for, is this development, build, and run parity of our software. So unifying those can help with that. But probably most importantly, we at Heroku have spent a lot of time developing this technology to securely run your web application. And so we have some really nice containerization technology with LXC, all hidden to you. You shouldn't have to worry about it unless you're interested in this stuff. But for me, I want to reuse the same service, this LXC service, that offers secure running of your web applications to securely run the building of your web applications. And so, could try to take the same control stuff and install it over here, but really the best way to do this is to self-host this service. So can do another little demo here. Slug compile, we call this slug compiler. So this is how we bundle code, some Ruby code for the Heroku runtime. So again, excuse my chicken scratch shell scripts, but here's the meat of the thing. We, somewhere in a Heroku dyno, need to bundle. We need to install bundler, or maybe it's already there, and bundle install. And so here, just copy the source over. So this is kind of just a theoretical exercise where I can take this application. This is Aloha Ruby. This is a show-off presentation and app. And I'm going to have it compile itself on the platform. So hopefully the demo gods are OK. So this should look somewhat familiar. Receiving the push, even though not actually pushing anything. Here it's just rsyncing some stuff, fetching a language pack, and now we're into our good old bundler, and it'll bundle all the dependencies here. And so this is an important step. Bundler is incredibly important part of the Heroku experience and the Ruby experience, namely because of things like this. We actually have to build some of these gems with native extensions. So this is, again, where we're going for this build, run, development parity. So if you need native extensions for your application, we need to build these somewhere on the platform. But again, so this shows, just Heroku run is more than capable of doing bundle install. So, and maybe this should, look a little similar to the LLVM Bootstrap example. Like really, again, this kind of generic Unix system for executing arbitrary code. So that's pretty cool. That something, just finally got the whole system moved over to the platform. So when you are doing a git push, you are always talking to a Heroku app, one of the more complicated apps on the platform. So leads the question, something we ask all the time at Heroku is, what else? What else can we, get rid of? So, big red X through these guys. So really, pretty much any one of these rectangles that represents a server is up for self-hosting. So the API, if Heroku can run Rails apps pretty well, if the API is a Rails app, maybe we should get that running on the platform. That one's been tricky for a couple reasons, which I'll get into in a second. Something like the message bus, perhaps. This is a service running somewhere, but it's really just a process. Maybe we can run that on the platform. It turns out, it's thin start is a web service. Why not Redis start or Postgres start in a dyno? Some tricky routing problems there, but actually not insurmountable. People usually ask, what about the router? If you can figure out how to do that, come talk to me. That will be the holy grail of the cloud singularity, I think. But of course, all these represent really interesting puzzles. So like I said, the API one's been tricky. There is a really complicated Bootstrap problem there. But we've figured this out for a number of our services. So the Postgres service, it uses Postgres as a data store, and it can provision and monitor its own database. That's pretty cool. Likewise, PG Backups, that's the backup service. It also uses Postgres and backs its own database up. And likewise, Slug Compiler, since now that's a Heroku app, when I git push Heroku for that, it'll compile itself. And so these can, puzzle is a nice way of saying it. These can also be disastrous if things go wrong. If I break Slug Compiler, if somebody breaks Slug Compiler, how do I release a new version of it that has the fix? But something, as we started going down this path at Heroku, it became very clear that we do look at this as a puzzle. These are just engineering challenges to solve, just because there are some reasons why you wouldn't want to do this for certain things, but if you just treat it as a challenge and something we can fix with engineering, it turns out we can actually solve those and kind of head down this path of self-hosting. So really, in conclusion, hopefully you can see through all these examples that self-hosting, it's just a goal for any complex system. The human body, cloud platform, a compiler. It's definitely something to study and think about for your software, your services, your tools, and that you just get these gains in efficiency and really good way to test that your system works and is correct and that has consistency. So really quick, some references here. A lot of this is classic computer science, compilers and compiler generators in '96. Really, really fascinating. Slow if you need something to fall asleep to, that's the one. This is a really cool one. Have you guys read Reflections on Trusting Trust? This is in the ACM Classics, one of very, very classic computer science paper by Ken Thompson. If you recall, used GCC to bootstrap LLVM. So he has a really, really clever philosophical question, which is, okay, well, do you really trust GCC? And I don't know, I'm just using whatever's installed on the system. Very, very cool demo of poisoning, one of the original versions of GCC, where it can add a backdoor into anything it compiles, and in a way that you can't even know that this is there. So that's a really fascinating one if you like to study the puzzles that come up here. And so that's it. I'd be happy to answer any questions about this or Heroku or surfing. No, I can't do that one. But thanks. Aaron?
If you forget about your servers, do any of them ever get lost?
The question is, if you forget about servers, do they get lost? Amazon is really good at losing servers, it turns out. They just vanish. We have lots of big, scary things in our administration tools that say, untracked server, and they do get lost a lot. Yes?
I thought it was a read-only file system. How do you do the compile?
Right. So Cedar is not read-only anymore. Surprise. And then you've always had a temp file system. So in this case was copying everything over to temp. But you can, if you do Heroku run bash on Cedar, you can write to the main file system. So don't save persistent data there. That's a bad idea, but we've backed off making it read-only.